In one of the earlier videos, I think it was the first video, when talking about the transfer function representation of linear time invariant systems, as a disadvantage, I told you that they don't give information about the internal dynamics of the system. So this is an important point, and I would like to explain that in this video. Okay, so let's define internal stability. A system is said to be internally stable if all the transfer functions from all exogenous inputs to all internal signals are stable. Okay, well, this may sound a little bit redundant. You may think that, well, if I have a closed-loop system which is stable, then why should I care about anything else? Well, that is not really true. You have to pay attention to internal dynamics, as I will show here. The transfer function representation may hide some problems internally in the system. Let's see what the problem may be on an example. Let's take a look at this system. We have a plant and we have a controller, and some transfer functions are given for the plant and the controller. The plant has two real poles. One is unstable at +2 and the other is stable at -1. And the controller is of type PI, and the gains are chosen such that the controller has this transfer function. Okay, so now let's take a look at the loop and closed loop transfer functions. The loop transfer function is these two multiplied together, which is this transfer function. And the closed loop system transfer function turns out to be this one, Ka over S squared plus S plus Ka. Okay, so when you look at the poles of this closed loop system, you can see that the closed loop system is stable for all values for all positive values of Ka. So yeah, it seems to be a nice controller, nice closed loop system which is stable for all values of Ka. But now let's take a look at this particular transfer function, the transfer function from the disturbance input to the system output. Okay, well, if you calculate that transfer function between this disturbance input and the output, it's given by this expression G over 1 plus K times G. And if you put G and K into that expression, you will see that that transfer function is given by this, S over S squared plus S plus Ka. So this is the denominator of the closed loop transfer function, which will be stable. However, we have an unstable pole in the transfer function. Okay, so this is what I mean by the internal stability of the system. So seemingly the closed loop system is stable, but when you look at the transfer function from the disturbance input to the output, you have an unstable pole, which means even if you have very, very small external disturbances acting on the system, because of that unstable pole, these will cause the output to grow indefinitely, even though the response to the reference command is stable. Therefore, since this particular transfer function is unstable, we call the system to be not internally stable. And if you look at this example, you can easily see that the problem is the fact that we have a pole zero cancellation for this unstable pole. In fact, when you come back here, when forming the GL, you have an unstable pole in G, but your controller has a 0 at the same location. So this cancels the unstable pole there. That's why you don't see that unstable pole in the closed loop characteristic equation. However, that unstable pole still exists in the transfer function from the external disturbance to the output of the system. So this example demonstrates that transfer function representation may hide some internal dynamics in the system. And also this example shows that in general it's not really a good idea to cancel unstable poles in a system. So if you have an unstable system and if you're trying to stabilize it, you should somehow move that pole to the stable region. And just putting a 0 on top of that to cancel that is not a way to stabilize an unstable system. Now, let me show you that if you study the same system in Statespace model, you will see that internal dynamics will be seen. Okay, so what I'm going to do now is I'm going to write the closed loop system using the Statespace approach. So this is also a good exercise for writing the models for interconnected systems. So let's go back to the block diagram. And we have two blocks, two dynamic blocks, and each block can be expressed using Statespace approach, using Statespace model. So this G is second order. So we will need two state variables for that block, and the controller is first order. So one state variable will be sufficient for the controller. And each block has its own input and output. The controller input is E, which is equal to R minus Y. The plant has input which is equal to U plus D. So you have to be careful about the inputs and outputs, and when putting these state space models together, you need to pay attention to that interconnections, and in the end you will have the state space model for the entire system. Okay, so let's first write the state space models for two blocks separately, starting with the plant G. So G has input U plus D, and the output is Y, so it's the transfer function between these two, and it's given by this expression. So first we can write this relation in time domain by taking inverse Laplace transform here, and that will give this differential equation. Now we're going to write this in state space form. Since there are no derivatives of the input signals, this is relatively easy. We can just choose the state variables as the first one to be the output and second one to be the derivative of that. And the next we need to write the state equations. We take derivative of the first variable x1 dot and write it in terms of the other state variables and the inputs. So the first one is straightforward because the taken derivative of x1 gives y dot, and y dot is already defined as second state variable. So the first state equation is given by this relation. The second state equation requires using the original this differential equation. So taking x derivative of x2 gives y double dot, and y double dot can be written using the differential equation of the system, and this gives y double dot is equal to y dot plus 2y plus u plus d. Okay, so y, we need to remember write this in terms of the state variables. So instead of 2y, I write 2x1. Instead of y dot, I write x2. And I just leave u and d as it is at the moment. Okay, so these are the state equations that correspond to the plant block. Now let's come to the controller block. The controller input is the error signal, the output is the control signal, and the transfer function is given by that. Again, we go back to time domain by taking the inverse Laplace transform, which will give us this differential equation. Here we have E, and the E can be written in terms of R and Y. Okay, so let me just point out that our goal here is to write the model in terms of external inputs only. And when you look at this block diagram, let me just clean this a little bit. There are two external inputs to this system. One is the reference command, the other one is the external disturbance. And these other signals E and U are internal to the system. So when I write the state space model, I need to get rid of these internal signals, and the only input should be the external inputs. Okay, so this is important. Unless I'm trying to write the transfer function from some internal signal to some other signal. In that case, obviously, that internal signal should be present. But otherwise, when you're writing the state space model for this system, you should only use the external inputs to the system to your state space model. Okay, so let's come back here. So the output is the control signal. This is my output. The input is error. And as you see here, we have the derivative of the input signal in this differential equation. So when writing this in state space form, you need to be a little bit careful because you cannot really choose your state variable as the output directly. So this is not this will not work because of the fact that you have the derivative of the input signal. Well, you can write the state space model directly, but I have this way of writing state space models for such systems, and let me just show that here. So I start with the original differential equation, and then you collect all derivative terms on one side, as I did here, and you define that derivative terms to be the derivative of your state variable. So I already used the x1 and x2 as state variables for the plant block, so I need to define a new state variable here, and I call that x3. So I define x3 such that the derivative of x3 is given by this relation. And since the derivative of x3 is equal to the collection of these derivative terms, I can go back from there to how I should define the third state variable. So in other words, I take the integral of this part, and that will give me x3 to be equal to u minus e. So this is how I define my state variable. And instead of e, I can use r minus y. Let me just keep it here for the moment. And the state equation for this third state variable is already here. So the x3 dot is equal to minus 2 times e. Okay. And the output of this block is u. Now I should also write the output expression. The output expression is u is equal to x3 plus e, or u is equal to x3 plus r minus y. But y was one of my state variables. In fact, it was x1, so this is minus x1. So the output equation is written in terms of x1, x3, and r. So now I just wrote the controller block in terms of in state space form, and I already utilized a state from another block, and this comes from the interconnection. So if I was writing the state space model for this block in an isolated form, then obviously I wouldn't be using this state variable. Instead, I will be using the input to that block, which is the error signal. But now I already started forming the interconnection, and instead of error, I used y minus r, and y is already a state variable in the other block, so I use that state directly. Okay, so here, right here, you see the interconnections being formed already. Okay, so I have now three state equations, x1 dot, x2 dot, and x3 dot, and everything should be put together. But before doing that, we need to make sure that all the internal signals are cleaned. And I think we already have some internal signals. Well, we still have some internal signals, right? U is an internal signal here. So I should get rid of that U, and I can do that by using this output expression I wrote for this controller block. So I take this U and insert it into that equation. And in x3 dot, I have y here, and instead of y, I can use x1 again, so this can be written as 2 times x1 minus 2 times r. And the details are here in the lecture notes. So I have three state equations, and this can be put in the matrix form. So this is the state space model. There are two inputs, the reference signal and the disturbance, external disturbance, and three state variables and one output, and that output was equal to the first state variable. And this is the state space model for that interconnected closed loop system. Okay, so as you know, the stability is can be seen from the system matrix, which is this 3 by 3 matrix. And if you compute the eigenvalues of that matrix in MATLAB, you'll get these numbers. And while doing that, I took the value of k to be 1. I think I forgot to mention that, but must be written somewhere here. Because in the transfer function, the controller had this gain Ka, and when I obtain this numerical matrix here, let me just add that here. The Ka is taken to be 1. Okay, and you see that unstable pole here, which we didn't see in the transfer function because it was cancelled by the pole of the controller. However, in the state space model, that unstable eigenvalue is still there. And when you wrote the same system in state space form, we can already see that there's an instability in the system. As this simple example demonstrates, state space model has the advantage that it maintains the internal dynamics of the system. So in this course, we will be using state space models for multi-input, multi-output systems. And that's why it's quite important for you to have taken a course on modern control, where you study the state space models and some methods for designing controllers based on that, like pole placement or LQR controller, things like that. Well, if you have not taken a proper course on modern control, I recommend that you study the state space models and some methods of that deal with these state space representations before proceeding further. So next, I will continue with some important aspects of state space models. But I think I will just stop this video here and continue with that in the next video.